Good morning to all the participants once again. The presentation that I am going to actually take you through is a general overview of the renewables, not deep diving into the issues because we have several experts lined up, a couple of them here in this session itself, which will go into the deeper aspects of this renewable energy integration. So here I would try to set the context of this renewable energy integration with some understanding of how globally it has been shaping primarily, and what are some of the high level challenges with the renewable energy integration. So I hope generally I flash this slide in most of my presentations. I hope most of the audience will agree with me on this. That's why we are here. That's why the renewables are being integrated at the moment. Of course, in 1970s, it started with different objective, though at that time the climate was not of the same concern that we have as of now. But for last several decades, climatic issue is the main reason that we are bringing in a lot of renewables into the system. And India is not immune to these climate changes. We have already had several experiences with the impact that this climate change is actually bringing into our various aspects of the life in the country. So emissions obviously comes the first thing in mind when we talk of the climate change. So you can see that globally we have roughly 38% emission is coming from the power industry. Of course, this whole energy system is a mix of different energy carriers, where electricity is one of the vectors, one of the carriers, and most of the time as we from the power background try to get more locked within the electricity sector itself, but there is beyond electricity sector other sectors that actually contribute to this carbon emission. But power sector is one of the major sectors which is the major contributor of the emissions globally and in India as well. While it is one of the major contributors of the emissions, it is also one of the key and major vector of the energy which helps us decarbonizing the system much faster and at a large scale compared to other energy vectors. That is the reason we are shifting several energy vectors to the electricity. We are electrifying transportation for the very same reason. We are bringing in green hydrogen for the same reason, putting that, bring that to the electricity sector, coupling that to the electricity sector. Heating and cooling, particularly in the European countries and cold countries, heating is being shifted to the electricity sector. Because of the very advantage that we have in the electricity sector, that it helps us in integration of the renewables which cater to these energy demands from different energy vectors. So in that sense, this electricity vector is becoming much more important, critical in the overall this gamut of energy system. Now, if we look at the overall contribution of the renewables in terms of the primary energy consumption that we have, you can see here 4% is actually met by renewables here. So we have a lot of way to go in terms of integrating renewables in the overall energy system across the world and in the country as well. These are some of the statistics of the renewables. This is wind. As you can see globally, as on December 23, we have around 1,000 gigawatt of wind. Why we start? I intentionally start with wind, because wind is the renewable energy which started much earlier than solar. If you look at the scale and the technology maturity level, wind is way ahead in terms of technology maturity compared to solar, even though solar later on actually because of obvious reasons overtook the wind in terms of the installed capacity. But wind was the first modern renewable energy generation that came into existence post 1970s oil crisis. And in line with the global trend, we are also integrating wind in the country. We with around 48 gigawatt as of today. Our history is also very old with respect to integrating wind. We have started in 1980s in the coastal areas, Tamil Nadu and other states, integrating the type 1 wind turbine generators, and we are continuing that integration of wind in the system. These are in terms of the cumulative capacity of this wind energy that has been added by different countries. But I would like to highlight that it is not only cumulative capacity. What is also equally critical is how much percentage of renewables you have in the system. If you look at the percentage wise, Denmark is number one country in terms of highest percentage penetration of renewables, which they have experienced even 120, 130% of the instantaneous power penetration from the wind, particularly solar is little bit there. And they have already achieved more than 50% of electricity share in 2020 itself, and they have much higher share of the renewables as of now. So therefore, both cumulative capacity as well as the percentage penetration is very important. India, we have, as I mentioned, 48. We are likely to take over Germany in some time in terms of the cumulative capacity. And then if you look at the solar power, solar, as I mentioned, it started much later than wind. Is because of its falling price and all that. Post 2001, 2002, the grid integration, the grid scale level solar PV plant started coming up at a large scale, almost 20 years after wind. And you can see that as of December 23, we have roughly around 1500 gigawatt of installed capacity globally in the solar capacity added to the system across the world. If you look at this, 2010 figures, we have around 40 gigawatt of installed capacity globally in 2010. And 2010 figure of wind was around 200 gigawatt. That is the difference between the maturity of the technology. 200 gigawatt versus 40 gigawatt of solar in 2010. Fast forward 2023, solar is way ahead of wind, and it is going to continue that trend as we move forward for these obvious reasons, because of falling price, availability of sun across the geographical region. And in India, as we are currently almost around 95 gigawatt of solar is already added to the system. We are also marching towards higher and higher penetration of solar installed capacity in the grid, with some states experiencing higher penetration compared to others, for example, Rajasthan state, and with the target of 500 gigawatt of non-fossil fuel-based sources by 2030, and the target is beyond that. We are going to continue integrating these renewables into the system. And that's where this renewable energy integration becomes, very important aspect. These are in terms of the cumulative capacity again, top countries. As I mentioned it again, India with 95 gigawatt of solar PV, we are likely to take over some other countries as we move forward in this journey. This is just one slide. Of course, the next speakers will talk more specific about the Indian RE sector. These are some of the states with higher penetration of renewables that we have in India. Rajasthan having the highest capacity here compared to other states, followed by Gujarat, Tamil Nadu, Karnataka, Maharashtra, Andhra, and MP. So some states, of course, are experiencing relatively higher share of installation of the renewables. Yes, so now renewables are there all for the good reasons, for obvious advantages that they bring in, for obvious cause that we have of the climate challenge, but they bring in along with them several challenges, technical, regulatory and other challenges into the grid operation. And that's what is the focus of this 2-day workshop, where different speakers will deliberate over different aspects of the challenges that these renewables actually introduce into the system, and what are the countermeasures and way forward to handle higher share of renewables into the system. Next slide, please. We can attribute, there are different classifications of the challenges that these renewables actually introduce into the system. This is one of the way of classifying them that we have felt is one of the ways. So you can see different attributes: intermittency and variability. These are the characteristics which we often hear when it comes to renewables, and these are very, very critical attributes of these renewables, because all across the history of operating the grid, we have been planning and operating the grid around the to actually cater to intermittency and the variability of the load demand. On the generation side, we have been actually relatively much in a better position to schedule the generation, conventional generation, around this variable load that has been there in the system. Despite the improving on the load forecasting techniques across the world, the variability cannot be avoided of the load. So one of the characteristics of the grid operation, the fundamental requirement of generation and balance at each and every instant, has been challenging even in the conventional system because of this variable nature of the load and the intermittent nature of the load. But the advantage we had in the conventional system was these dispatchable generators, where we could actually dispatch the generators as per the requirement. But now, by introducing generation from the renewables, we are introducing intermittency and renewable variability on the generation side as well. So that makes it much more complicated. Now we have variability and intermittency from generation and load side together, and then we need to actually balance out this generation and load demand in the system. So that's what is this variable and intermittent nature of a renewables attribute that actually leads to the how unit commitment should be revisited, economic dispatch should be revisited, what are the storage requirements that we have, and other aspects, countermeasures to address this intermittent and variable nature of the renewable energy generation. The other critical attribute is non-synchronous nature of the renewables. Leave aside the old wind turbine generators, type 1 and type 2, which are obsolete technologies now, though we have some of them already in the grid, at least till they retire or are repowered. But vast majority of the renewables that we have in the system are IBRs. So these IBRs actually are non-synchronous in nature. They do not have that inherent coupling that we have had with these conventional generators, conventional generator rotor and the grid frequencies magnetically locked. And that gives us a lot of advantage during the grid disturbances. There is an inherent nature of these conventional generators that support the grid technically. But that is lost here. That inherent nature of supporting the grid during disturbances is no more there in the IBRs. Because of this converter, which we say generally it makes the generation side blind of the grid, it does not actually support the grid the way the conventional generators support. So this non-synchronous nature of these renewables, IBRs, introduce various issues in the system, technical challenges into the system, which includes frequency stability issue, voltage stability issue, low inertia system, and other aspects into the system. And then the third attribute is power quality, which is becoming more and more critical at higher and higher penetration of renewables. These IBRs introduce various harmonics and other power quality related issues into the system, and then interaction between different controllers of these renewables, interaction between the controllers of the renewables and the conventional generators, all those, that dynamics actually becomes very complicated when we look at the system with higher penetration of renewables. This is just one measurement showing how the power exchange between Denmark and Germany is varying because of the wind variability over there. You can see a lot of variations in the power exchange compared to the earlier days when the system was mainly conventional. This is the effect of the variability of the renewables. Next. Similarly, we have the solar variability. Of course, it has little bit more predictable pattern, but if there is a dynamic weather change, it disturbs the whole dynamics of the generation from solar. It introduces a lot of variability in the system. In addition to that, uncertainty and intermittency into the system, and that, as I was mentioning broadly, is bringing into various challenges for the grid operator to balance out this generation load in real time operation. Next. Um, Inertia is one of the impacts that these renewables actually bring into. As I mentioned it, because of the non-synchronous nature, the rotating mass that we have had in the and we are having in the conventional generators is actually of a tremendous advantage for the grid stability. But then when we bring in these IBR in the system, this rotational mass is lost, including for the wind generators, type 3, type 4, both of them. We have every new wind power plant that is coming in India is type 3 wind turbine generator. Hopefully down the line when we have offshore, we'll have type 4. But as I mentioned, no type 1, type 2 wind turbine generators are there being added to the system. And these, even though there is rotational mass, but because of the converter interface, that rotational mass doesn't actually help the grid. So therefore, this diminishing rotational mass because of the IBRs that are getting added to the system is bringing in its own challenges to the system operation. For example, you can see here in this particular ERCOT case with increased penetration of renewables, how the inertia is coming down. And this is the case study we have done here at IIT Bombay, where for the same system, for the same generation outage, but with different penetration of renewables, you can see how the rock-off is actually increasing, how the frequency nadir is actually deteriorating further and further with the increased penetration of renewables. Next slide. This is one of the studies that has been done on Irish grid, where you can see for almost 28% of the time the system is technically insecure because of lack of sufficient adequate inertia in the system. Then Ireland had set some time back 50% maximum power penetration from renewables. Now they have increased it, and they were having curtailment. Of course, not only Ireland, but several countries. China saw at 1.11%, 12% curtailment from the renewables because of various reasons, particularly grid security. So therefore, that is actually another aspect that this inertia is bringing from the security perspective. Next slide. This is the similar trend that we are experiencing in the Indian grid. This is Western regional grid trend of the inertia. You can see even though we have a reasonable mass, rotating mass in the system, but the trend is same that I showed for the other countries. It is decreasing. The inertia is diminishing in the Indian grid as well. Therefore, it is important that we look forward into the system where we are actually increasing more and more renewables and how to handle this inertia issue in the system. In fact, the IGC 2023 has also specified specific requirement of the minimum inertia empowered grid operators actually to take countermeasures to ensure that adequate minimum inertia is maintained in the system. Next slide. Grid strength. We quite often come across some of the terminologies. This is actually, even inertia is a grid strength on the frequency side. Grid strength on the voltage side, short circuit capacity side, short circuit ratio side. So that is another aspect that is actually one of the very critical aspects of the challenges in the renewable energy integrated system. The short circuit ratio decreases in the system with the increased penetration of renewables, and then other issues are there. What is the correct way to measure the short circuit ratio in the renewable energy integrated system? How to quantify it effectively when there are so many renewables that are getting added in the system? So therefore, those are some of the other grid strength related aspects. When this renewables, more and more IBRs are getting added into the system, they bring down the level of short circuit ratio in the system, and there are several consequences that this low short circuit ratio actually brings into the system operation in terms of stability, in terms of voltage stability, in terms of oscillations, in terms of other control aspects that these renewables actually bring in by bringing down the short circuit ratio of the grid. Next slide. There are reverse repercussions also. So this is one of the studies we have done at IIT Bombay. The conventional generators also are having some of the impacts because of increased penetration of renewables. They do have issues. They do have some reliability and other impact on the shaft. because of these lighter grids, because of more fluctuations in the frequency, higher rock offs that the systems are experiencing. So there are some impacts on the conventional generators, also the interactions, that oscillation and other things that are into the system. Next slide. This is well-known issue for those who are working in renewable energy sector. Quite often you would have come across with the duck curve issue, which is very particular about this, specific about the solar PV integration. And this Casio has actually been one of the interesting case studies across the world. You can see the net demand, how it is, touching to zero, even going to negative in their system. Starting from, if you see 2015, the net demand here, and then moving forward here, you can see 2022, 23, the net demand touching zero during the daytime, and then having net demand zero, which is actually essentially, technically removing this, the conventional generators from the system during these hours. And then in the peak hours, you need a lot of non-solar PV generators up in the system. That makes it much more challenging in the system, in the overall system operation. Next slide. South Australia is another interesting case study across the world. They are having quite a bit of renewables into the system. You can see here, wind is quite a bit in the added in the system, and net demand you can see has gone to minus 927 megawatt recently. So that means actually they have quite a bit higher renewables that are coming up, and because of it is a relatively weak connection with the rest of the Australian grid, there are several issues that this particular pocket of the Australian grid is actually experiencing because of the higher penetration of solar, wind and solar PV. Of course, they have reasonable significant penetration of rooftop PV solar as well. Next slide. This is again overall Australian grid is experiencing quite a bit of penetration of renewables, wind and solar. Again, as I mentioned, rooftop solar is quite a bit there in the system, and a lot of issues have been reported already with the rooftop PV and the overall generation of the system. Next slide. Denmark, as I mentioned, it is one of the, along with Germany, one of the pioneering countries that brought in a lot of renewables initially, particularly wind. And you can see a lot of share of electricity that is coming from the wind. 72% of share from the wind generation in last year has been actually catered from wind. So a lot of wind is actually there in the system. Of course, they have the advantage, in Nordic grid, we generally say that they have this pumped hydro storage country, Norway, which is actually supporting them a lot in integrating renewables, because during high wind in Denmark and Sweden and on the Germany side, the pumped hydro storage is becoming actually effective in Norway. And then during the low wind scenarios, the pumped hydro storage generates electricity back, and the electricity prices accordingly vary in the Nordic market. Next slide. There are several case studies, several events across the world that we have, but this is, in the interest of time, I have just added this one of the this event case study. Some of you might be familiar with this, but these events, it's not new. We have also had some events in the Indian grid in past few years, but they are not very new. Other countries which have been integrating these renewables have been experiencing similar issues in the past. 2008, 2009, several large-scale events have been reported in several countries because of all these aspects of the renewables that are there. So this is one of the recent ones, 2016, where there was a blackout in the Australian grid. There are a lot of wind in the system in a South Australian grid, and they are interconnected with two tie lines you can see here. One is AC, Haywood, and then we have this DC, HVDC linked with the rest of the Australian grid. It was doing fine before that storm hit that region, and because of the storm there were back-to-back several voltage events in the system, around 6 voltage events in some around 88 seconds time. And that actually brought down the power generation from the wind, which actually overloaded the this AC tie line because HVDC hit the limit. And as a result, because of the overloading of this tie line, it was tripped, and eventually the system went into the blackout in 2016. Now there was a lot of debates around this. What is the reason for this blackout? Can we blame the renewables for this? Is there something else? Can we blame the grid operator? Should we blame some other stakeholder? But the issue is not whom to blame. The issue is to understand and recognize the challenges with the renewables and then address those issues. Next slide. So here there were multiple recurring faults that took place, which generally across the world, except a few of the grid coders, had not anticipated that we will have back-to-back several faults in the system. So generally the grid coders across the world talk about one low voltage ride through. But this particular event experienced several back-to-back events. So as a result, the grid code was not very clear about these back-to-back LVRTs. And the wind power plants accordingly actually reacted. Of course, there is a debate on how they could have responded and how they should not have responded. But there is no specific mention of recurring LVRT ride-throughs in the system, in the grid code regulation. And that's what was one of the major reasons of this. So therefore, post this event, they brought in the requirement of recurring LVRT requirements, voltage ride through, including HVRT, LVRT in the system. So therefore, those were the issues that actually led to the blackout of the system, and eventually highlighted some of the issues, some of the unanticipated events and the responses of these renewable energy plants. Next slide. This again, I would assume a large section of the audience will be already familiar with this. This is bringing in another extreme side of the weather impact on the renewables in Texas because of this extreme wind, freezing issues, and early outages, ice accumulation on blades, gearbox, and other components of the wind turbine generator, which led to the offline wind capacity of around 14.6 gigawatt. This was one of the very specific issue that was experienced in this particular grid. And then, of course, again the countermeasures have been brought in, suggested. But what is again this is highlighting is there are some unknown or you can say unanticipated events that need to be actually taken into consideration when it comes to the renewables in order to have adequate resource adequacy and the grid security and stability maintained. Next slide. For all these different issues that we have in the system, there are various countermeasures. New technologies are emerging. Grid forming converters, many of you would have heard, are addressing have a potential to address several issues that we have talked about, grid strength and other related aspects. Grid forming converter technology simply emulates the behavior of the conventional generator. As a result, it does help in many ways. But then that's not all. Every time when we introduce new technology in the system, there are new challenges that they bring along with that. If you look at the next slide, so this is showing how this grid forming based wind power plant is actually supporting the grid in terms of inertia and others. This is a field demonstration of the same, where because of this tie line tripping, the plant is actually providing the inertial support or fast frequency support to the grid because of this grid forming technology that has been implemented in this wind power plant. Next slide. So these are some of the issues with the grid forming also. So when we talk about introducing new technology, we have to be aware of the potential challenges that they will also bring in along with them. And it has to be accordingly planned. For example, you can see here there are several issues that are mentioned here in terms of inrush current requirement, injection of fault currents, inherent inertial response, there are, for example, we are talking of the strength in the grid. Grid forming IBRs are expected to strengthen the grid. So low short circuit ratio issue can be to some extent addressed through this grid forming converter technology, which is technically very correct. But there are in high strength grid, the grid with high SCR ratio, there have been instances where it has come out that grid forming technology actually has a detrimental impact when the SCR is high. So there are various challenges associated with even grid forming technologies. Therefore, it is very important to understand what countermeasures we are suggesting, what countermeasures we are bringing into the action, and what are the potential consequences and new technical challenges that they will potentially bring into the system and plan it very effectively. I think that is bringing end to this first introductory presentation. With this, I would conclude my presentation. Thank you very much for your patient listening.
Thank you very much for the nice introduction and very say good afternoon to everybody. Thanks to the IIT Mumbai and the Professor Jake and the lab where this is being done today, this workshop for 2 days, for inviting me, for giving me this opportunity to share some of the thoughts with all of you. So basically, we all know that Indian grid is a very large grid and world's amongst the largest synchronous grid in the world, wherein the entire country is interconnected. And so therefore, there are different type of challenges, different type of opportunities everywhere in all the sectors are there. And we are going towards, as everybody has mentioned, that we are going towards the large scale energy transition from the fossil fuel based economy to the renewable based economy. This is all fine because in any case we have to go towards the net zero, and this seems to be the way forward. But in between, we also need to take challenges that all the time our grid remains reliable, our grid remains secure, and that is our prime responsibility. But if any of the event happening in the grid, it impacts a large section of society, and then all the different type of issues rakes up, whether this is because of renewables, because of any other things. As in the last session you have seen that in case of Australia there was number of discussions at the different level that why it was there and what different technologies would have done. So therefore it is very important that we understand each and every nuances of that, and they are all new things. So definitely it takes some time to absorb those nuances, but it is the very, very happening time in the country, in the world. And every electrical engineers is now, basically they will be doing much more electrical engineering nowadays, simulation based studies, which were hitherto not given that much acknowledgement, that much, but now this has become extremely important, that we actually need to work on very electrical engineering, very simulation based studies, whether they are real time, they are say based on the dynamic studies or the steady state studies, or further to that even we have to go further beyond that, and optimization, all those things has become extremely important. So coming to the today's presentation, let us so basically my presentation will include the dimension of grid which we are all having. We must know the dimension of our grid, and all the time we should take pride out of it that we are a largest synchronous grid in the world. And India's journey with the renewables, how we have, at what stage we have reached, and then in energy transition roadmap, what we are looking forward to in the next coming years, say coming 5 years, or say by 2047, where we want to go, and the building blocks for resilience and what we require basically. And I will also give you some of the actual happenings in the system, actual case studies from the system, and then the way forward, how we should go ahead. So this is what the numbers speak about our grid. More than 250 gigawatt we have met in the last May month, in the May 24 last year. Basically, we have met 250 gigawatt on a particular day. That was on 29th of May. And then we have also met the demand of 5.4 billion units and on the, that particular day. We have a very 40 or 50 lakhs kilometer of EHV transmissions, and that is more important that we have around 206 gigawatt of renewables, including large hydro. So non-fossil fuel, you can say, we have 206 gigawatt presently in the system. And we have around 118, as you all know, that we have been demarcated in the 5 regional grids. So there, between the regions, we can import, export around 118 gigawatt of electricity from one region to another. This is cumulative one, not from, say, from west to any other. There are different terminologies for that, how much actually safely we can transfer from one area to another area. It is important that we have also 14 HVDCs in the system. So these HVDCs include back-to-back as well as high voltage long distance transmission. There are 800 kV and 500 kV HVDCs. And we have around 4.5 gigawatt of international exchange, mainly with Nepal, Bhutan, and Bangladesh. With Nepal and Bhutan, we are synchronously connected. With Bangladesh, we transfer through HVDC as well as through one radial line from Tripura to Bangladesh. We have around, 3 power exchanges. This is also unique in a sense that we have 3 power exchange for the same electricity area. An entire country is one. Basically, you can transact from any area to any area in these power exchanges simultaneously. There are different type of challenges and different type of issues, how things are being segregated between different power exchanges. And then we take, say, more than 102,000 market transactions, and then we have 6,000 plus market participants. So very big system we had, and this system has to be run reliably. That is the challenge. This is what has been the situation in the country, as there was that how things has moved in the entire world. This is what how things has moved for the renewables in the country. If you see to 2015, you must be knowing that there was Government of India's, there was a target earlier of 20 gigawatt of RE in the system. And slowly after the 2014 new government came, and then there was again these targets were increased to 200 gigawatts, then now it is 500 gigawatts. And then we have slowly increased. As you will see that the pace of increase in solar capacity has been tremendous. This is a very high rate of growth in solar capacity. And now we have around 90 gigawatts of solar capacity in the country, and around, say, 47 gigawatt of or 48 gigawatt of wind. And cumulative, this will come to around 142 gigawatts of wind and solar, what we call as variable RE. Other than this, also there is a hydro would be there. So all those if we include, then it will go to more than 200 gigawatt. Highest instantaneous penetration has been to the around 33%. So that is also very important, that we have been saying that whenever this will keep on increasing, this penetration will keep on increasing, as you have seen in the different part of the presentations, that if this will keep on increasing, we will have more and more challenges to take care. But we have already reached to 33%, one third of energy coming from the renewables, from the solar and wind only. Not, I'm not talking about the hydro in this. If we include hydro, that will go further up. So this has been on 13th of September. And highest instantaneous wind penetration has been around 15%. And highest solar penetration has been 31% approximately. So these are real numbers. This is how we have been operating. Some of the states, some of the, say, country you might have been seeing that they have all, say, become green. Everybody has become green, but they are also part of larger interconnect. Similar is the situation in our country. In some of the states, are more than 100% renewables at one or other time. They have met entire their electricity from the renewables only. So this is also the situation in our country also. So it is, sometimes people say that my country is entirely say 100% renewables, but they are part of larger interconnect. So as a part of larger interconnect, as a country, entire country, we are one large grid. In this, there are some of the states which have crossed this penetration level of very high penetration. This is where we want to reach. By 2030, we want to reach around, say, 293, or we can say 300 gigawatt of solar and 100 gigawatts of wind. So this is a very, very huge number. And we feel that during that period, very high, we will require a lot of storage from, not only from the pump storage as well as from the battery storage also, or any other technology which will be, say, can get developed in the next few years. And then by 2047, we are targeting around total installed capacity of more than 2,000 gigawatts and solar of 1,200 gigawatts as well as wind of 450 gigawatts. So this is again a very, very huge numbers. And so these numbers will definitely has a very huge challenge. Till now I have not said only about this may be from the developer side that these numbers has to come in the system. But what these will impact the system, how present impact has been there in the system, I will go now onward. So basically what has been there in our present system, that few things are extremely important. Some of the areas of our electricity or our country are blessed with a lot of solar and wind potential. So therefore, in those areas, more and more solar and more wind will be coming up. But what problem this creates, that if it is very concentrated, said we are targeting around, say, more than 100 gigawatts of solar by 2030 in Rajasthan, and around 40 gigawatt of solar in Khavda area of Gujarat. So these are very concentrated areas in which large part of the solar or renewables will be coming. This have several type of challenge. One thing is that in the solar, in the Rajasthan area, what we have been finding that because of short circuit ratio, there has been a lot of issues, a lot of voltage fluctuation in Rajasthan area. And what we have taken a lot of operational initiative that, okay, we will not switch on, switch off any of the reactors during the high solar hours. That has been working fine. We have also taken so many other initiatives that let us come out with the clear that what these different solar or wind power plant need to do, need to provide how they need to be complying with the standards, what present standards. So there has been a lot of debate that whether these standards need to be complied and how these need to be complied. So, but this has now become almost certain that these standards has to be complied. There is a very clear-cut first-time charging procedure by the Grid India, as well as this is being followed, and from the planner side also, from the central transmission utility also this is there. I will request all the states people, STU as well as SLDCs, that let us enforce this type of, you can always improve on this. Let us enforce this everywhere, because these issues will keep on coming at all the level, and our grid being one, if anything happens at any place, any part of the grid, this will impact each and every one. So therefore, it is extremely important that we all take care of these regulations. So what has been that we have mandated that they need to provide the reactive power. As per the as per the CA standards, they need to provide 33% plus minus 0.95 power factor. They need to run anywhere as per the requirement of the grid, not at their will that they want to run. As per the requirement of grid, it means that you might have seen Mr. Manu Srivastava, that he is saying that when voltage is low, you need to inject more VAR. When the voltage is high, you need to absorb VAR. So similarly, these resources at the interstate level or the intrastate level, at high voltage level, these need to respond to the different type of situation in the grid. Another challenge has been a lot of, harmonics issue has been also there in different, we are facing different type of harmonics issues. So there have been, again, a lot of work is going on, and more or less, again, situation is that people has to comply with that act. We have also, has been a working group which has come out with the sum that how it will be checked that they are complying with the harmonics issue. Another important parameters has been that this, as per the CA standard, this need to be checked each and every year. That what is the harmonic percentage at each substation, and also by at the each of the power plant. So, but this is not happening. So we also again need to work towards whether all the transmission utilities, they also need to measure the harmonics, actual real harmonics happening at their each of the substation, each of the EHV substation. Then only we know the baselining, and then only we know that where it is coming from and where we need to take action and what action need to be taken. So that is another area, important area where we all need to, I will request all the SLDCs and STUs to work towards that, and these from all renewable generators, all the OEMs as well as all the developers to be more proactive towards this, because this will not only impact you, but it can impact everybody. I should say reverse that, not only impact others, but it will impact you. Then only people should realize that it is very extremely important, that because it will going to impact you. Your plant can also go out and can create problem. So that has been the issue. And then another issue has been in the grid, that when we are not able to say forecast this winter months in the morning hours, I will also come to that how the load shape of the country is. But say during morning hours we have high demand period during winter months because of heating load coming on the system. So during this period we need that these renewables should ramp fast. But say because of cloud cover or because of say a fog situation in the northern region, sometimes during morning hours these generation do not come in on the system. What will happen? Because at that point of time our load ramps from presently 120 or 130 gigawatts to 228. Today's maximum demand has been at 228 gigawatt as on all India basis, and in the night time it was at 3 a.m. it was around 130 gigawatt. So this high ramping is required in load. Similar, we have to ramp up all the resources, and say solar generation will ramp to around say 50 gigawatt, maximum generation from the solar which is being monitored. Again, there will be rooftop solar and all those solars, but at what is being monitored at the control center, that is around maximum has been 55 or 56 gigawatt. So say it ramps from 0 to 50 gigawatt. Say from it start ramping after, because sun nowadays comes after 7. So say 7 to 11, it will be ramping to 50 gigawatt. But this ramping is important. 50 gigawatt ramp coming from the solar, and if does not come, if there is any delay in this ramping, you will have lot of issues in the system, and low frequency as well as say if this comes up high, if you have taken up other resources online, you will not be able to back down, because they again could be ramping constraint to bring them down. So that is another challenge. Therefore, the forecasting the renewables is becoming extremely important. All the OEMs, all the developers, everybody has to pitch in. It is not that sometimes we feel that it is okay, it is the problem of the grid, let grid people should solve it. But it is everybody's problem. We all are part of the grid, whether this is X generator or Y generator, everybody is part of the grid. If anything happens to grid, everybody will suffer. So therefore, everybody has to give his part of service, and therefore every developer need to do these properly forecasting. Not only it is required from the grid stability purpose, we are also doing this forecasting. We are recently signed a MOU with the IIT Mumbai for working on the forecasting also. So that in any case is there. We are also coordinating with IMD and NCM RWF, but that is not sufficient. Only 1% doing for this entire big system, it will be extremely difficult. Each and everyone has to do it. That is how the DSM regulation has been framed, that everyone has to forecast properly. And then only it can move fast, because everybody will be working, we will learn better. We will learn, definitely we will improve our understanding of technologies, everything will improve. A lot of young people in the IITs, etc., everybody is talking about the AI and the machine learning. These are the areas which can be extremely important for those areas. Not only say, not AI can't say all the times may not do, but say local weather forecasting, or say from satellite pictures, inferring some of the results. These areas could be extremely good for the further research. Apart from that, we are also having some issues in the Rajasthan area, wherein say LVRT and HVRT issues has been flagging out. This now with the we have suggested some of the mitigation measures and some of the say changes in the settings of these LVRT and HVRT, and this has given us some results. This definitely has improved, which were earlier LVRT and HVRT events. Any of the fault taking place near to this Rajasthan area, we used to lose large chunk of generation, and that again was creating a lot of issues. But now fortunately, with these changes in the settings of these inverters, there has been some improvement. But this is not the end, because each and every manufacturer is having a different philosophy, and we all need to, as a utility, as a developer, we need to understand those nuances, that how this inverter really is working, what are the challenges in this inverter, how we can tweak that it can support the reliability. But it is not the end. Basically, still we are having some of the issues in the LVRT and HVRT because some of the plants, say within the plants, there is one inverter will be nearer to the point of interconnection. Some of the inverters will be far away from the. They will have different voltage. They will be looking at different voltage, because at the LVRT and HVRT they will be local phenomena, not done from the PPC. So that is why how to further education, further interesting things are required to be done in that area. We have already has a MOU with IIT Bombay, with Professor Jakir, to investigate further in this area and how we can further simulate and what type of actions need to be taken in that area so that our grid becomes more reliable. Further to this, there also has been, because of these PPC makes are different. LVRT, HVRT, we do have certain regulations, but for PPC presently there is not much regulation in entire world and also in our country. We have been pitching for that there need to be some regulation for the PPC, some standardization for the PPC also, because presently different manufacturer of PPC are having different, say, time delay. This time delay also can cause number of issues, because say there could be racing for MVR between two plants, and that could create a lot of problem, lot of oscillations. So we have, as a operational measures, we have taken some of these measures, that how we can do, how can mitigate those things. But this is a very, very challenging area. We need to come up. Another issue has been in these power plants that their internal communication is generally on Modbus. So that is not that fast enough. And that is the main reason for the delay in response of some of these plants for the reactive power. So there is a lot of work is required, a lot of say research is required in those areas to further come up with that, how we can do that simulation, that modeling, or that changing in the settings of different PPCs and the different delays, how we can make them uniform or slower or faster, because sometimes faster can also become a problem. If it is very fast, it can become unstable, right? So these again, a lot of work would be required in that area. Another interesting issue has been that these say we have different type of, because they will be coming in particular area. So if any natural calamity takes place, lot of high voltage lines are there, HVDCs, because 125 gigawatt moving away from the Rajasthan area would be, and that too in the 3-4 districts. So very high concentration of the transmission system would be there. And this transmission, if there is any natural calamity, one is that any cloud cover comes, we will lose a very huge chunk of generation in that area, which is presently also happening. But still we are not that high, around say 21, 22 gigawatts of solar in Rajasthan area. And rest say in Gujarat area. But still problems are there. But these problems will much more magnify these challenges. But I should not say problem, because these are challenges. We all as engineers, we are all as a people, we have to find out solutions of these challenges and bring that how we can mitigate those challenges. So these challenges will increase manifold. So one from the say weather related event, another also whether it is say any thunderstorms, or say we have been losing number of transmission lines, number of tower collapses has been happening. If this happens to in these areas, this will be catastrophic, because any tower collapse or anything, it takes say at least 10-20 days to months together, and it has been taking lot many time in the state network rather than in the interstate network. At least there are some timeline specified by the regulator, and so therefore people still try to do that. But intrastate systems, we have been seeing that there is a very large time gaps, and so sometimes there will be a huge curtailments of possibility of huge curtailments of RE could be there. So therefore that is also important. And another area of challenge has been already mentioned in the previous session, that there would be inertia issue. So in northern region, also in Rajasthan area, we are seeing that there could be an inertia issue, system strength issue. SCR has been at some of the stations has been quite poor. As per the CA regulation, it talks about that it should be minimum 5 SCR ratio at any of the node wherever we want to connect any RE. Minimum should be 5, but at some of the locations this has been going down 5. So there is also another requirement that how we can improve the system inertia. So lately there has been a committee in northern region. It will be working for all the, basically it is just a direction towards that. So some of the action they have taken, that some synchronous condensers are required in the Rajasthan area, some will be installed, and then we will move forward toward that area. So that will not only give us the inertia, but they will also give us short circuit and further strengthen the reliability of the grid. Another area of this, say, LVRT and HVRT has been the response time. Though these regulations, LVRT and HVRT say that they need to remain right through this. But how much time they need to support, whether say if any fault is there, we definitely, our units, machines used to give lot of wars to the system, so that whenever fault get clears, voltage ramp up fast. But this voltage support from these renewables has been a cause of concern. Though there was a notification from the CA that this is how it should be, during this period they should prioritize the reactive power. But what is happening that because of very high response time, say there is a fault has taken place, you all know that as per standards, this fault at 400 kV or 220, say 400 kV and above should clear within 100 milliseconds. But actually it clears between 50 to 60 milliseconds, say 20-25 milliseconds for the relay to operate, and then all breaker to operate 20 milliseconds. So around 40 to 50 milliseconds the fault get cleared, and 10 millisecond you can also count for the communication between the relay and the breaker. So this is 50 to 60 millisecond fault get cleared generally. Then what if this response time of the inverter is so low that it is say 100 millisecond? This is giving MVR after 100 milliseconds. So fault has already cleared. It has not supported during the fault time. It is giving the lot of MVR after the fault. So it will definitely deteriorate the situation. It will go into the HVRT mode. High voltage it will go, and inverters will go under HVRT, and if they are not properly tuned, again we can have a problem of the HVRT, and the inverters can trip. This has been happening lately, but now with some of the improvement in settings we have been tried to overcome. Still the response time has not. So this also requires that the response time should be clearly delineated in our regulation. So this is our one of the response requirement, that these regulations, as already was mentioned that by JSMNRE, that we need to change regulations slightly faster. So these technical regulations also required to be changed fast, and new learnings has to be incorporated in that. So these regular updates of the strengthening to make regulation standard future ready and is extremely important. And so that any learnings in between, we are able to incorporate in those things, and further at least new installations will have those functionality available. Resource adequacy and flexibility, this area is also very important. That, as I have already mentioned, that say if we can lose 10-20 gigawatts of solar right now because of cloud cover, so you need some other flexible resources to take up that job. Or say because of cloud cover, small cloud cover, there is in a large area, say Rajasthan area, 10 gigawatts of solar goes out. You will have to ramp up fast some other resources during that period. So how fast resources can present, our regulations say that at least minimum of thermal plants, they can ramp up at 1% per minute. And they can go up to 3%. As per CA regulations, they can go up to 3% per minute. But most of the plants are now operating with 1%. We need to further go higher and higher up from the convention, because our maximum large fleet is from the thermal power plant. But other resources, whether they are hydro, whether they are gas, whenever they are running, they also need to contribute towards that, because they can ramp up faster. So that area is important. And resource adequacy, what we mean, that all the time frame, whether we are talking about say year ahead or 5 year ahead, or say year ahead, a month ahead or day ahead, or in real time, all the time frame we need the resource adequacy assessment, that how much ramping. Presently till now this was not that much challenge, because of coming of renewables we have this challenge that each hour, for earlier what was there, that how much say 250 gigawatt I have to meet maximum. So for 250 gigawatt, whether we have enough resources or not, enough generation is available, that generation can be always, because slow ramping up, this can go up to 250 gigawatt, another time we can back down that generation when demand is slightly lower. But in now all the time frame, each hour could be different, each hour could be a challenge. Even say during the night hours, we could face a challenge. As again I will quote one example, that in this year during the August month, you might have seen that during all say Sundays, we have a problem of high frequency during the daytime. All along say all Sundays of August month, we have a problem, because there was good rainfall in the entire country, and therefore load not being that high. But other say generation, solar generation, wind generation has been quite high during that period. So high renewables in that period and low demand. We have backed down all the generations, say thermal, because that is needed during the evening time. As you might have seen the duck curve about all those, everybody talks about that during evening time this will come up, again load will come up. So you need resources. So what was happening, that during that time, most of the say interstate plant were running at 55%. This is what the current regulation says. Current CA regulation also talks about that plants should go to 40%, and they have talked about that there is a timeline that each and every plant has to go in next few years to 40%. But that is not happening at that pace. So that area also need to be taken up on priority. Number of state generators in number of states, still there are some of the plants which are not going to say 55% also. So that is another area of challenge, that each one of us to need to work toward that they need to at least start going to 55% and later on to 40%, because this, as more and more solar comes on the system, next year you might have already seen that next year we are targeting about, this year itself we are targeting about more than say 25 to gigawatt of solar in this financial year. 20 gigawatts say in this calendar year has already been mentioned by the JSMNRE. Maybe 25 to 30 gigawatt we will be we are targeting for in this financial year. So this much, this solar will keep on increasing, and also from the rooftop solar and the say Kusum side, also there would be a lot of increase of the generation from the solar. So this problem will keep on increasing, that we don't have enough down margin available in the system. So that area also is extremely important, and I will request because a lot of state SLDCs heads are there. Let us keep this trying out. Each and every day we have to try out this and convince people that this is extremely required for the future system operation. I have been already mentioned some of the things, that robust transmission planning, not only from the say short circuit ratio, from the inertia perspective, but also from the disaster resilience, that whether it has to be disaster is how we can make the system disaster resilience. If any disaster takes place, how quickly we can come up. So that type of technology, that type of planning, this should be ingrained in our system, that it is not that somebody is telling, but it is ingrained that we have to look for these virtues, these things in our planning procedure, so that our system will definitely, those things will make our system more resilient. And we have also been saying that let us spread out. If it is remain very say localized generation of renewables, it will create some or other issue. So let us also think about the policies or working in such a way that these renewables are spread out entire country. So therefore, they are different places. So as far as rooftop is concerned, or say Kusum is concerned, in different areas, this is quite helpful. But problem with this would be that how we monitor that, how we get the information that how much rooftop is there in say any particular city, Delhi, Vadodara, or any say Mumbai, how much is rooftop is there. If on cloudy day this generation will not be coming. So our forecast for the load forecasting has to consider that. So at least numbers we should have, that how much is the rooftop, even if we are not getting the real-time data, but we need to have the numbers that how much rooftop is there in each of the area, so that we can properly take care of that in the load forecasting of that particular DISCOM or that particular state or region or country as a whole. So that is extremely important. And with this, another issue will be coming, that if we have say data capturing of all these, everybody is talking about this, that this can be captured now because technology is available. So another challenge in that would be that how we mitigate the cyber securities. As more and more say digital devices and more spread of these digital devices, digital data collection would be there to the every individual, there is more and more challenge, because our surface area is increasing. Attack area surface would increase. So how we can mitigate those challenges of cyber security, that is also extremely important, that how we manage those things. If we talk about that each individual house owner will invest so many things on the cyber security of its solar rooftop, it is very difficult. The people won't be doing. So what technologies do we need to deploy for that? That if this goes to certain data center somewhere, we keep them small, and then later on each and everything of cyber security is taken care of, so that intentionally or wrongly somebody may not switch off this. Say if somebody switches off entire solar generation, rooftop solar generation in particular area, that could be catastrophic. Similarly, with the smart meters, that is another area of cyber security challenge. When this data goes to, it is all fine that this data goes to some data centers, and then from there it can be utilized for different purposes, that is fine, but there are also another difficult cyber security challenges there. If they say somebody hacks that data center and goes into these smart meters and then disconnect all the loads, this could be again catastrophic. So that areas also need to be taken care of, and suitable actions has to be taken. Sustainable ecosystems for the equipment testing and modeling. That area is also becoming extremely important. We presently have, say, number of testing agencies from outside India. And that also creates a lot of issues. So we need to, because we have now become, government is also giving a lot of subsidy on Make in India, on the PLI based scheme. So in these areas also, whether they are developer or say entrepreneurs, I will request that come in this area. This is also extremely important that we have these simulation capabilities in-house in the country. We have these testing capabilities in-house in the country, and they understand, so will understand so much nuance. Our knowledge base of everybody will increase. Presently, say if anybody comes from outside, they may be having some knowledge, but they may not pass on that knowledge to us. We may get some reports and understand, but if our people are doing these jobs, definitely we will be having much better ecosystem and much better system. This ecosystem will also improve day by day. So that is extremely important. In this area, we need to, a lot of entrepreneurs could be there in the IITs, and that area need to be taken up faster. Forecasting I have already mentioned. So with this, as far as the technical standards has been there, the interconnection point or point of interconnection, there has also been debate on this, but now it is well settled that it is the point at which its plant will getting the connected to the utility system, either STU or CTU or DISCOM system, point of interconnection. All the compliances has to be monitored at that point. Then reactive power capability test, that as I already mentioned, 0.95 plus minus, they should be capable of delivering that. There has been, because as you know, this has impact on the ambient temperature. So some of the inverters say 3.1 MVA inverters there. At 35 degree, it may be able to deliver 3.125 MVA, but when the temperature increases, its capability decreases. So that also, it has to be these designs has to be compatible with the ambient temperature, and the Rajasthan or say Gujarat and Khavda area, these could be very high temperature areas, and therefore our installation should be able to take up with the ambient temperature issue in those areas. And when these large scale RE will be coming in Ladakh area, the low temperature issue has to be taken care of. Frequency response, this is presently in our grid code that more than our CA standard, that more than 500 megawatt plants has a capability that they can take the signal from the remote, and they should be. But this frequency response, each and every plant should have at least capability they should have. When in future this comes in a grid code, state grid code, say national grid code, that these need to provide those ancillary services, they can always be hooked up. But this functionality need to be there, that they need to, based on frequency signal, they should be able to ramp up or ramp down their generation. And what type of, I will tell you that we have also done a AGC pilot with a solar generation. First AGC pilot for a solar generation. We all know that we have around 70 gigawatts of thermal and gas and hydro plant connected to the AG system at national level. And that is working quite fine, except that the amount of reserves are limited. Each and every plant is presently, except for one plant, everybody is only changing by 5% only. So, and we have opened this gate that any plant in the country can participate in this AGC, whether it is, say, intrastate or interstate, anybody can participate. So, except that this has to have some investment they have to do for the taking that signal from the National Control Center. Coming back to the discussion point that we have conducted an AGC pilot on one particular power plant in Rajasthan area. They have been kind enough to support that pilot. What we have found out that during different periods it's ramping. Basically our standard CS standard said that 10% per minute you should not ramp. This limitation is from the fact that you should not ramp very fast or very high so that other resources cannot ramp. From that perspective this limitation was done. But this is a limitation. We found out this will be different in different inverters, but this inverter we found out that this was a limitation, and even it cannot go up to 10%. We have done some with 5% ramping only, so this was somewhat successful with 5% ramping. Further, on certain particular days, it was not able to even ramp with 5% also. So again, there are a lot of learning is required from the inverter side. Inverter OEMs and all those people also need to further interact. So this ecosystem, as I was talking about in this area, if OEMs are our own countries' OEMs, definitely we will have much better interaction and much better understanding, and this area will also be required a lot of understanding. But this is what a successful pilot, and we hope that in future, at least for down reserves, if they cannot go up, say they will be operating at maximum power point tracking, MPPT we generally call that how much, whatsoever resource, whether wind or solar is there, they all want to maximize their generation. That is fine, but at least if frequency is running high, we can always get them down. So that down reserves margin could be utilized from the renewable set, well, rather than directly curtailing them. This could be a better way of doing that. Active and reactive power set point, I have already mentioned that this can be done, presently being done from the PPC, and PPC should have capability to it be done from the remote, say from the control center. And how much time does it take? This also is very important in this area, that how much time it takes if it is done remotely, because that will, in entire control loop, that will impact. We all those control engineers, we must be knowing that any time delay, gain and time delay, these two things are extremely important, and then pass filters, etc. But at least these two things are extremely important. They can make the system very sluggish or not up to the mark, or very fast or oscillatory. So therefore, these things we need to, this is also another area for the electrical engineers to look into, to deep dive into this area and get a lot of good things from that. Weather extremes I have already mentioned, the ramping capability as we have already discussed, and the power quality as harmonics we have also discussed. This is, power quality is becoming more and more challenging when large IBR based resources are available in a small area. Say different number of, in the entire, we have been knowing that at say high voltage level, there have been very less harmonics because of these harmonics not being there. With our systems, they may be getting bypassed. But with these IBRs coming in one particular area, they all generate a lot of harmonics. And with HVDCs, we have been having, say, filters, and they were acting as a harmonics pass filter. But with this also, we need filters and different type of designs and different working in that area, so that these harmonics do not disturb other plant. Otherwise, it can be catastrophic for some of the plants. So these standards and regulation to keep pace with rapid technological advancement. Each and every day, new OEM will come. They will have some other philosophy. So understanding these philosophy and notifying our philosophy a priori, that this is what we want from these resources. If you want to give anything extra, let me try it out, test it first at the inception level itself. That type of collaboration between the academia, between the, say, OEMs or, say, utility people is required for better things in future. New type of, say, IBR based load of data centers, green hydrogen, they are also in the pipeline. And in very near futures, they will be also coming up fast. So what type of services, again, regulation presently, or say electric vehicle, or say battery storage systems, also not that elaborate regulations are not in place. We need to, at very fast pace, we need to create regulations for these type of resources also. Apart from this, these technical regulations, they will also require that how they can participate in different type of, say, whether they can increase or decrease their load during different time, if requirement is there, how they will be able to do that. That is also important. And a lot of, say, presently till now, mainly the, say, bulk consumer or anything was coming at the state level, generally connected with the state grid. Now they can come at interstate level also. So what type of, see, obligations they have towards the grid? Presently the state, generally they have different regulations that from the reactive power capability or from other resources, they have been having some or other regulations. But now then they come to interstate level, they also, regulations also need to specify their obligations towards the grid, towards the society. Grid is nothing but a society. So that area is also important, and we have to, as Professor Jakir has mentioned, that we are grid forming inverters. A lot of talk is there about the grid forming, that in the low SCR area, they can work very fine. They can, lot of problems which we have been facing with the grid following inverters, grid forming inverters probably will be able to sort out those problems, those issues. But again, we have to learn a lot, and we have requested some of our friends in the RE sector that let us at least do some pilot. Let us understand that how these grid forming inverters work and what additional things they can provide, or how they are better than the grid following. So I will request the different, say, people in the RE sector, let us have some of these pilots, and let us come out, have some learning on these. Regarding the net zero target for the what we have, though I have already mentioned, there's some more elaboration towards it, that indigenous single unit IBR or WTG testing facilities, accredited certificate agency within India, plant level testing facilities and agencies. Presently, plant level testing facilities are quite minimal. Only some of the testing we have been able to, as reactive power or some other, but still we need to do so that actually how the plant is performing. That is becoming important. Earlier you might be knowing that most of the people even were not giving the model, the steady state or the dynamic models were not got by the planners as well as the operators. But this is where we presently are there. At least people have started giving these models. There are certain lacuna in those models, certain issues with those models, but still at least people have tried, are now trying out. And as a movement, as everybody tries out, definitely we will learn more, better. And we will have a better ecosystem all along. And that is why I have already requested the SLDCs and STUs to also ask for those things, so that there is a movement toward this area and we have a better ecosystem in the country. Modeling and technical consulting agencies in India, availability of suitable simulation tools with system planners, operators and other stakeholders. Presently, generally we should not say any agency or any type of software, but these are required. There are different softwares available. Some of them are the Indian made, some may be foreign. We also need to work in that area also. That is also required, though presently it may not be very easy to do that, but we also want that people should go in that area also, that these software also are the made in India. Building up skills and competencies in modeling and simulation studies, aspects such as logistics, requirement, etc. They may be, so these are the IGC 2023 is already specified the periodic testing, whether they are for the conventional generator or the RE generators. So periodic testing has been now cornerstone. Everybody has to do those testing. So that is also important, that let us plan properly at different forums that how we will be doing these testings and what will be the time frame, which plant will be tested in what time frame. So a lot of work is required in that area. Validated model preparation, when we will do testing, field level testing, these validated model, that how, because sometimes what is happening that some models has been submitted, but when we see actually this may be working fine, all LVRT, HVRTs, everything is fine, or this will be come up within 1 second, more than after the fault clearance, within 1 second, say if voltage goes up, then within 1 second it should reach to the 90% of the pre-fault megawatt value. This is what the regulation says. But number of plants has not been able to do that. So it means that in this simulation, they are perfectly fine. They are reaching up to that level. But when actual, there has been difficulties, there has been issues. So that it means that the model which has been submitted is not actual what has been on the ground. So this area becomes extremely important, that we have capabilities to test, and we need to make then validated model from the actual field testing. So this is what I was referring to in the August, 25th of August. This is one Sunday when we have no reserves down margin available in the system, and frequency ran for the more than 5 hours at our threshold level. So this is what we need to think about future, and a lot of flexibility requirement would be there. And if we say from this curve that you see that a lot of ramping requirement would be there. This is of May month. If you see the similar curve for the current month, January month, you will see that morning hours, as I already mentioned, sir, from 130 gigawatt to 28 gigawatts. So very high ramping is in the morning is required currently. So if any problem is there in any of the resources, it will manifest at a very significant level. So this, you see that on this particular day, the prices in the market were quite low, and we have a very high RE generation on this particular day, and the net load was quite low. And in contrast to that, there was a day when there was very little RE in the system. So we have very high prices in the market and almost flat. If you see net load curves, or the green one, will almost flat in that case. So this type of issues will keep on happening more and more, and on daily basis, predicting them and taking countermeasures becomes important. This is what I have been saying, that these capacity in one particular area. So we need to have a system strength issue, and natural disaster we need to take care. We have already discussed this thing, and because this EHV and ultra high voltage line, another issue, all of you might be knowing that we have to open the line during the night time. These 765 kV lines, because they generate lot of VAR when they are loaded below their surge impedance loading. So night time almost no load, so we have to switch off large number of lines and again switch on large numbers of line during the morning hours for these areas. So another area of work is there in southern region. We worked out that we can have nighttime resources. These IBR based resources can give us the nighttime performance when they absorb or give reactive power based on the requirement during, even though there is no generation available, active power no generation, but still they can provide the reactive power capability. So that capability is there. What is creating a problem of when more and more high voltage line will be coming up, we have to presently also we have to switch on, switch off 30-40 lines in that particular area daily. So this work, any miscalculation, any delay and anywhere can create problem, because that will hindering the solar will be ramping up on their own pace. And if there is any delay of synchronizing any line, then we are in trouble because some other section will get overloaded and we will be trouble. So they all has to be very meticulously has to be done in a very fast time window, very small time window. These has to be done. So that area, whether we can utilize those resources. So I will definitely request from the RE plant developers that let us think about that capability is there. We have tested that in the southern region, and that could be utilized for the grid. So we have to open less number of lines, and everybody will be get benefit out of that. But this area of that large concentration of these resources in one particular pocket is another challenge, which is not, I should not say slowly we have to reach to that level, but that also need to be kept in mind, and how we can say do these things in a different areas, that should also be thought about all the time. Future planning is that cyber security, system integrity. Another issue with this I forgot to mention is about the protection system. Presently, our say 765 kV, 400 kV, or these lines having a distance type of protection has been there, and then there is a negative sequence or say positive sequence, or all these protections we are quite familiar with. But these IVR based resources, that protection also need to be thought about, that how this protection will work in these areas, and a lot of work is required in those areas as well. So this is for the presently still we are able to manage. Not much issues has come out from that area, except that some of the protection system in some of the plants has been that say rate of change of frequency protection enabled in somewhere, or somewhere other type of protection, some frequency threshold protections were there. Those type of issues were there inherent, but at least from the line protection or these type of protection issues, not that much protection has not come, but they will soon start manifesting. So in that area also there has to be enough work has to be there for the how this protection will work reliably in high IVR scenario. Energy storage and new technology also need to be taken care in the optimizing the transmission planning. So that is another area. Till now we have not been, say, even this first synchronous condenser, as I have already mentioned, is coming up, would be coming as a transmission asset. Till now we were not that much amenable towards these assets, rotating assets coming in a transmission system. Similarly, at present day, this storage-based technologies may not compete with the transmission because they are quite costlier, and transmission is not that much costly. But we should think about that, whether they can come as a transmission services also or not. At least each and every generator, they should come up with some sort of resources, some sort of storage, so that they can, basically they will also get a lot of benefit out of this type of system. And as JS Amanari was also mentioning that presently we are, there is a talk about that, okay, let us go about something that with tenders wherein they can be utilized, same connectivity, similar, say daytime solar is there, another time some other generator can, or other resource can come in that area. I think others I have already discussed. So with this, this of one day when 8 gigawatt of solar generation we lost in 1 hour, so that was the cloud cover. And presently it is, say, of 2023 scenario, so it was very less generation, only 16 gigawatt around generation of solar in Rajasthan area. Now it has become 21, 22 gigawatt, and this will keep on increasing. So when this goes up and up, this will be larger and larger contingency would be there. So this type of contingency, what we have, presently we take a contingency of say 4.5 gigawatt in non-solar hours and 7 gigawatt in solar hours. But this contingency, size of contingency will keep on increasing. So whether that much resources would be available, how these will be available is next challenge. And this, you will see on the right hand side, there has been lot of, say, forecasting error on certain particular days, and this error value will also keep on increasing. So this error value also we have to improve. Everybody has to improve, and a lot of time, say, as somebody was in the break time was mentioning that some of the generators may be because they know that this is what the band is, say 10% or 15% or 5%, whatever band is there for the no same rates will be they will be getting, plants will be getting the same rate. So what they will say, generally they know that okay, why I should err on the such a side that if I get more money, if I say over schedule, definitely I can get more money, either I sell in the market or so I will get more money. And if I am on the by any chance I am on the negative side, I am at least 10% or 5%, whatever margin is there. So up till that there is no issue. I will be paying the same amount of money, so there is no issue even if. So all these calculations would be done by different agencies, that how we can get more and more help from the current set of rules or regulation. Everybody does that. There is nothing wrong in that. Everybody should optimize it. But this is what the challenges would be from the system side, and how we can take care of those things to curb such type of practices. With this, sustainable, so what these are the pathways for the future. Sustainable ecosystem for equipment, plant, balance between robust compliance, verification, and effective queue. This is also another challenge that everybody is talking about, that in our country we are saying that 30, 50 gigawatts every year we will be integrating with the system. In some of the developed countries, this process has been very slow. There is a very long queue. Say, as I have already mentioned, that now people are giving these, say, model in a 3 months to 4 months in advance. Earlier this was also not done. So now they are able to give in 3-4 months in advance. But in other countries it takes, and we are able to give them connectivity, the first time charging, everything in that time period. Earlier it was, in some of the countries it takes, say, more than years, more than, say, 2 years, 1 year, 2.5 years, all these things. So queue management. So that is called as queue, how we can integrate more and more people. And the robust compliance. It should not be that we are taking our guard anywhere down. It may not manifest today, but definitely it will manifest some or other day. Any relaxation, anywhere we give, this will come back to us. This will harm us more than what today we can gain slightly. So that need to be kept always in mind, that let us do things properly. Let us have a better compliance verification system, and more better, and everybody learns that from that. It seems that on one particular, some days it seems that okay, it is very difficult to do that things, but once we start doing those things, once we have a capability to do those, becomes very easy, and this becomes very straightforward, and a lot of learnings also takes place from that. So do that. Identification and periodic review of resource adequacy and flexibility requirement, we have already discussed. Robust, optimal and timely transmission planning, resilient network, multifold rise in number of generation and visualization of situation. This is also another important area. If we say just a small example, presently our deviation settlement mechanism talk about that in the denominator, say generally we will say error in percentage of schedule. Generally what we know that what is the error. But presently for the renewables, DSM talks about that in the denominator it would be the available capacity. Available capacity means how many inverters or how many wind turbines are there in the system at that particular day or that particular time block or that particular hour. But I have not seen much people, generally it is installed capacity only. Many people are not changing it. That installed today, my 2 turbines are not working because of any reason. So this area, that when this becomes, say, very high numbers in any one plant, there could be very high number of wind turbines, very high number of inverters. So having the knowledge, having that which is not working, which is fine, which becomes extremely difficult, and which say inverter is giving a problem. So that situational awareness, here is also a lot of AI and ML can give a lot of insight in that, and that is also area to work on. Forecast accuracy and multidisciplinary collaboration we have already discussed. Regular review and strengthening of the regulations we have already discussed. So with this, I thanks and I will be happy to answer any questions you have. Yeah.
From the morning session, we are seeing the global scenario, global perspective in the integration of RE. Then Porwalji has briefed us about the national scenario, national integration of RE. I am basically from the generator side, and now I will come to the state of Maharashtra. So, state of Maharashtra in general, and my company, Mahagenco in particular. So, we are a 13,220 megawatt company. We are known as Maharashtra State Power Generation Company Limited. It was earlier MSEB, popularly known as Mahagenco. Now, we have got the installed capacity of conventional 10,212 megawatt. Thermal is about 9540 megawatt. And gas is about 672 megawatt. So total 7 stations are there. Thermal constitutes about 76%. Gas, one station is there. It constitutes about 5.08%. Renewables are 3008 megawatt. Hydro is about 2580 megawatt. It constitutes about 9.5%. Total 25 stations, small and large hydro stations. Solar is about 428 megawatt. It is about 3.24%. There are some agro schemes, solar agri schemes, and some EPC projects owned by Mahagenco. This is the vision of Mahagenco, and this is the mission of Mahagenco. So these are my conventional power plants. Bhusawal is 1210 near Jalgaon. 210 megawatt one plant, 500 two plants, and now we are now commissioning one 660 megawatt plant at Bhusawal. The trials are going on. At Chandrapur, we are 2920 megawatt, 5 units of 500 megawatt and 2 units of 210 megawatt. Khapa Kheda near Nagpur, it is 1340 megawatt, 4 units of 210 megawatt, 1 unit of 500 megawatt. Koradi near Nagpur is 2190 megawatt, 1 unit of 210 megawatt and 3 units of 660 megawatt. Then Nashik 630 megawatt, Paras near Akola is 500 megawatt, Parli near Aurangabad is 750 megawatt. So our generation is scattered, base load is scattered all over Maharashtra. Now the gas plant Uran, it is near Bombay. It is a combined cycle power plant. 108 into 4 gas plant and 2 into 120 waste heat recovery boilers. So this is total combination of Mahagenco. Next. Then in renewables, we have hydros 1956 at one location, Koina. It is near Chiplun. So there are 4 into 70, 4 into 80, 4 into 80, 4 into 250 and 2 into 18. These plants are there at Koina. Then Pune Hydro Circle, we have got Pune Hydro Circle. There are small plants shown here. And we have got Ghatgar Hydro Station, Ghatgar Hydro Circle near Nashik. That the capacity is shown here. Out of that, Ghatgar 2 into 125 megawatt, those are the pump storage plants. We are operating, actually operating pump storage plants in Maharashtra. So these are the solar combination. This is the EPC one. We are the first in the state to install solar in Maharashtra. We have done 1 megawatt solar at Chandrapur 15 to 20 years back. I think 18 years have already passed. So one started from 1 megawatt. Now we are moving to 280 megawatts EPC, and these are the Mukhyamantri Saur Krushi Vahini Yojana for the farmers, 148 megawatt. So we all know that Maharashtra is by energy consumption is competing with the international players. Maharashtra is the leading state in terms of overall power use. It is highest and more than Gujarat, Uttar Pradesh, Tamil Nadu and Odisha. Our peak demand in 2024 was 29 gigawatt. Aggregate demand was about 185 gigawatt. And now this per capita electricity consumption and per capita gross domestic product, urban population and employment pattern, this relationship will increase the generation and demand in the state of Maharashtra. So we have planned that by 2030, the consumption in Maharashtra will be about 280 megawatts, and we will surpass all the other this type of countries. So the requirement up to 2035, the CAGR was about 4 to 4.5% pre-COVID. Then during COVID it was 0. Then post-COVID from 22 to 24, it was the energy requirement raised from to 8 to 10%. And we have planned in the first phase the rate of energy requirement as 6 to 6.3%. The requirement for Maharashtra will be 280 billion units, whereas by 35 it will be 370 billion units. Also the peak demand, this is the basic requirement, and the peak demand will be about 35, up to 35 will be 60 gigawatt. Because Maharashtra is progressing and 50% FDI is coming from the national level, as compared to the national level, 50% FDI is coming to Maharashtra. So the growth rate of Maharashtra will be higher. Considering that, these projections are made, and this is planned by the state government. Now we all know this. We are signatory to the Paris Agreement, COP26 commitments, then your G20 commitments, net zero emissions, and 50% from the non-fossil fuels by 2030. So these are the Government of India policy, RPO obligations given to us. We have to use this with the fossil fuels. So these are the targets. India 12,000 gigawatt for solar, and capacity target 319 gigawatt of solar and 110 megawatt of gigawatt of wind by 2030. Now coming to Maharashtra. Maharashtra's peak demand growing at 2 gigawatt per year, much higher than the state's current capacity addition rate. It is about 29 gigawatt now. It is expected that demand to grow at 6.5%, thereby Maharashtra's peak may reach 37 gigawatt by 2027 and 45 gigawatt by 2030. So installed capacity is 46 gigawatt with a historic capacity addition of 1 gigawatt per year over the last 6-7 years. Now, to cope up with this demand, we have to next. So these 39.2 gigawatt to FY35, financial year 35, it will reach up to 60 gigawatt installed capacity. Next. So national peak also is in line with we are in line with the national peak. State is in line with the national peak. So this national load curve index, monthly peak index, nationally and state-wise, we can see that we are following it. So these are the requirements in million units to meet the renewable power purchase power obligations. Next. So while planning this up to 2035, there are some assumptions for the next 10 years. First is the demand. Peak demand will be about 42 megawatts. Agriculture demand will be about, shifting here and there, 5,000 megawatts. Green hydrogen is coming. It will require powering about 9,000 megawatt. Pump storage plants are coming. It will require about 6250 megawatt. data centers are coming, they will require about 7,000 megawatt. So total requirement during that 2035 will be 69,282 megawatt. And this capacity requirement till 2036 will be data centers plus additional requirement of data centers, PSPs plus contingency requirement of PSPs, and green hydrogen and their contingency requirement. So we will have to have surplus power during that period. Also, the load will be increasing, particularly Mumbai Metro, MMR region, Pune region. There will be huge impact because of these data centers. PSPs will be in this Konkan area and Western Ghats. Green hydrogen will be in this Konkan region or the Raigad region or the near to the ports. So all the load centers will be western, particularly beyond the Western Ghats and this Konkan region. Next. Second assumption during this is higher demand intensity leading to sharper peaks, even by 10 to 20%. So there will be fluctuations in the peaks. Demand profiles will stagger due to unexpected rainfall, extended dry spell, due to environment. There may be some changes, and reduction in capacity of transmission lines because the transmission constraints are there. Though our colleagues, Transco colleagues, are planning for future ready transmission by 2035 to meet this demand. Also, the thermal capacity we are having, that is 30-year-olds, we are 35%. So after 10 years, these capacities will have to be retired. Then 15 to 30 years, we are 14%, and less than 15 years, we are 51%. So this 35% capacity of my total conventional energy will retire in the next 10 years. So this is the roadmap for Genco. Now, state. So these are the three scenarios we have calculated. So how much capacity and in what areas Maharashtra can go by 2035. So three scenarios were created, looking at the options available, looking at the time and this period of commissioning, and the cost of the generation, what we can offer to the people. So there these three scenarios. So initial we can see high thermal scenario so that we can meet the base load. So 14 gigawatt of thermal in the first scenario to be added. So whether to go ahead and what is the economics further. So there the cost is increasing. So then high RE, high storage. So incorporating storage and high RE. So what is the scenario? And high RTC and moderate storage. Storage kitna rakhna hai and RTC kitna rakhna hai. So here the RTC type 1 and 2 is added in the third scenario, and pump storage, particularly RTC, other RE and this storage 14% and solar about 39%. This is our plan. So this will be the overall mix by 2035. Now solar is 9.447, 26 and 70. So with this, the thermal is coming down to 41% and solar is, this RE is going up to 56%. This is the plan. Now further capacity additions in we are retiring some units by 2035. So we will be adding the base load of 660 megawatt at Bhusawal. That unit is under commissioning. 2 660 units, thermal units are planned at Koradi near Nagpur. 1 800 megawatt unit is planned at Chandrapur. And 1 800 unit is planned at Paras near Akola. So only this much capacity addition of thermal is planned from our side by 2035. And then commissioning of 3,225 megawatts of pumped hydro plants and PSP projects and solar capacity additions. So what will be the implications? So Porwal Saab has already explained flexible operations of thermal plants. We have to bring it down to 40%. Now we are running technical minimum at 55%. We are going it up to 50%. but the national policy is 55%. So we are backing down the power in the solar hours, and we are raising the power in the non-solar hours. So this coal-fired plants, flexible operation requires to be done. New wave of energy efficient system, because when we are operating the machines on low load, the efficiency of the thermal plants will decrease. So that care we have to take, or otherwise the pollution will also increase when we are running at the full load and we are running at the partial load. The environmental impact will also not much change, as well as the efficiency we will lose. So this aspect is to be taken under consideration. And then circular economy, whatever is the waste generated out of all these things, that should be circulated in the economy. So this transition we are achieving by 2035, that we can achieve with the following planning: meticulous planning, capex infusion, and efficiency improvement of the existing plants. So these are the challenges whatever earlier we have discussed. This is the flexible operation, what is required, how we are doing it. Now central government is coming with the 40% flexible operation rules. So that requires again capital investments. So that is to be seen. Mr. Soni Saab and his Transco team is doing a good study in Maharashtra. They have come up with some new ideas. I have seen one review and one data collection from them. They are coming with good solutions where to implement the flexible operation, which plants of Mahajanko or the state plants needs immediate flexible operation, which plants are not required. So where to infuse the capex and where not to infuse the capex. So these type of studies will help us to go further for making the decisions. So further there are guidelines from the Government of India to not to shut the old plants. You have to run the plants by 2030, and I think it will again go by 2035 like. They have asked us to go for the renovation and modernization of all the thermal plants, because the base load, the demand of India will be increasing. Whether this RE capacity will fulfill the demand or not, that is to be seen. So Government of India don't want to remove the coal-based generation from the grid. In fact, they have asked us to add about 80,000 megawatt in the next 5 years to all the stakeholders of India. So these are the planning given to us for R&M of the renovation and modernization of the plants, our old plants, that they have given us by 2043. So biomass, we have to use this biomass as a, there is compulsory from the government to use the biomass in your coal firing. So this policy is also there. So we have to, this rates and transportation cost is already fixed by the government. Availability of the biomass in Maharashtra is the great challenge now. Now the transmission constraints, see, because in Maharashtra the load centers are Mumbai, Pune and Nashik side, and the generation is in the Vidarbha region, particularly Chandrapur, Nagpur, Akola, Paras area. So the power is flowing from east to west. But with this RE and with this further demand in the PSP requirement in the Western Ghats, then your data centers requirement in Pune or in MMR. So the power flow will be from, and your generation in RE will be in the north side, because Nandurbar and Dhule area, this area of Maharashtra is solar. There the radiation is more and solar plants can be more efficient there. So this transmission corridor now will change from the east-west will be there, but at the same time from north to south there will be transmission corridor, and our these transmission guys will let you know what is their planning for next 2035 by 2035 next. So these are the just discussed hotspots shown, where there will be the high demand, where there will be the generation, data centers were coming, urban development, upcoming industries. Then agriculture solar scheme. This is one of the biggest scheme in Maharashtra going on. By 25-26, about 15,000 megawatt of solar solarization is going to be happen in Maharashtra. Already the government has awarded contracts. This is done by the CM Solar Agri Scheme 2 under this scheme, and government is very aggressively monitoring it. So these are the earlier discussed grid stability and base. Porwalji has already discussed these things. Then requirement of capex. So everybody wants generation to come. The huge capex requirement will be the most important thing. So generation will require 200,000 crores. For storage will require 20,000 crores. For transmission will require 50,000 crores. This is state-wise. Then distribution requires 60,000 crores. So this in the next 10 years, this much of investment will have to be made in the power sector. So then circular economy, so, we all know this. Then green hydrogen, and Mahajanko is doing one pilot green hydrogen plant at our Bhusawal. We have 500 kW, 20 Newton meter cube hydrogen plant. And we are planning 50 megawatt hydrogen plant in Uran. That process is also in final stage. So all these academics, OEMs, policymakers and lenders, these are the four pillars of this progress of next 10 years. So everybody should work together and go for improvement of the state. Next. Thank you.